Good afternoon. I hope that you enjoyed the post-K talk during the lunch and the K computer tour. So this is the last chance that you could actually look at the healthy K computer, because they will retire sometime very soon. So we will have the replacement for the next few years to the post-K. And this session is about big data assimilation. So big data assimilation is the project that we started 5.5 years ago. And the reason why we have this session here now is that some of the funding for this conference is from this project budget. So that's a part of the reason why we have this session. So in this session, first I will introduce what we have done in the past 5.5 years. And then, based on those achievements, what we are looking for the future. And then each of the PIs in this program, this project will present 15 minutes each. And finally, Dr. Seko from Meteorological Research Institute, he will present the project for the post-K. So first I will briefly talk about what we have achieved so far. So this project was motivated by this type of event that happened in Kobe. This is a river, small river in Kobe. And only after 10 minutes from this, even people were kind of playing there and became like that in 10 minutes. And 5 people, unfortunately, were killed by this. It's not flooding, it's just a lot of water. So as you can see that Kobe has the steep mountains. So it's really quick if we have rain in the mountains. Only in 10 minutes it can happen. And there was no warning. People could just step up here. No flooding. So it's not flooding. So if people are outside of this river area, safe. So this is really a challenge. So this type of event is caused by the rapidly happening heavy rainfall like this. So this is an example, different rain system. But this is an example of the actual observation from the phase array radar. So every 2 minutes, we have this 3-dimensional rain image. So at 5:30 local time, this is Osaka. We started observing this first echo, and that became like heavy rain in the sky. And in 8 minutes, it falls to the ground. It's a heavy rain already, and it lasts for like 5 minutes. And then the next system here, just next to this convective cell, started developing around this time, and after 8 minutes, it reached to the ground. The heavy rain reached to the ground. So everything happens only so a lot of changes in 10 minutes. If you observe only once in 5 minutes, it's too slow. So we have this radar system that was implemented in Osaka University in 2012. So about 6 years ago. This can observe 100 elevation angles, 30 seconds volume scan. It's really amazing. So this is the actual image from that radar. So every 30 seconds, we get the volume scan. So that's why we can see this very smooth motion. This is great. Another type of new sensor is Himawari 8. It's easy to see that this is more frequent, colorful, and precise. That adds up to 50 times of more data than the previous generation. So this is orders of magnitude more data than the previous. So we have big data from new sensors. And about 6 years ago, it was the time that people started talking a lot about big data. So the Japanese government started a program, the funding program, focused on the big data. So we propose to combine with these big simulations with big data assimilation. So that's how we started this project on big data assimilation. So we have a fortunate combination of the K computer. At that time, it was still young. Now it's old and retiring. But it's like the human year of 10 years may be equivalent to 1 year. So it's like 80 years old. That may be equivalent to like 80 years old in human age. So it's time to retire. And we had a brand new phase array radar, and still under construction Himawari 8 6 years ago. And we proposed to combine these two, all of these things. And it took us about 2 or 3 years to develop this system on the K computer. So we have the data every 30 seconds. The aim was to use all of the data every 30 seconds, 100-meter mesh. So we had to run 100-meter mesh model, 100-member ensemble, and every 30 seconds data assimilation, every grid point. It's a crazy idea. So we developed this system, and every 30 seconds we get the data and make the forecast. And this is the second result, actually. This looks very beautiful, and it's Kobe. That's why I'm showing this. So this is the actual observation. This is what we get from the K computer. These are all from the K computer, but at different resolution or without data assimilation. So this is very nice. And I will skip the details of this, because this is posted on YouTube, and I would like to ask you to look at on YouTube, because we have one of the highest views. And yeah, we try to. So if all of you click, then this will change. So anyway, so the details you can look later. So we get these really nice results. So the scale is like 5 kilometers here, and we are here, and 10 kilometers. And we have this detailed structure of this convective system. And we can really do it very nicely. And that's very nice. And it took us 3 years. And we also assimilated the Himawari 8 all-sky infrared radiances. And this is the case without using this Himawari 8 data. If we assimilated this Himawari 8, then we get this cloud image from the simulation, from the computer. And we can clearly see the difference of the clouds. And of course, it gets closer to the observation. We have many of these results already published, so you could refer to those papers. And another thing that we explored was to run a large ensemble. So we run 10,240 ensemble members, LETKF, and each of these dots. So we plotted all of the 10,240. And if we look closely to these 16, then we can see the differences. The southern hemisphere is more different because we have fewer data. Northern hemisphere are similar. So this is nice to see the sampling error reduced. And also we have more resolution for the histogram. So all of these that we have achieved based on these big data and big simulations. So we explore these, pushing the limits, the big ensemble or the rapid update and high resolution. and we try to explore the future of numerical weather prediction. That was our mission here, having this huge supercomputer that the operational centers will have maybe in the next 10 years. So we have kind of the access to the computer resource 10 years ahead of time. So what we need to do is to explore what we will do in the operational system 10 years later. So, so we developed the system, but we didn't run it real time. So to run it real time, we need to improve the compute speed. When we started developing a system, it took us more than an hour to run a single cycle. And the data comes every 30 seconds. And if it takes an hour to process that, well, it doesn't really make sense. We cannot run it in real time. So we tried to improve the computer time. And we had a midterm evaluation in 2016. So we worked very hard in that year. And the 6 months of development made it like 6 times faster. So we reached 10 minutes. Good. But 10 minutes, it's still 20 times slower than what we really need to do. So this year, we had a final evaluation. As I said, this project is ending. So we already finished the final evaluation. So with this year, we worked very hard for the 6-month period. So this is the experiment. When we did it last year, January, it took us like, so we also did a lot of acceleration from this time, more than 1.5 minutes. So it's here. So we have different access here. So this is 1.5 minutes. But what we would like to reach is here. And as you can see, we did it, but we had to reduce the resolution to 250 meters. But we did it. So this system can run in real time. So but what's the impact by reducing the resolution? So this is the actual observation. 250 meters, we reduce the resolution. Or 100 meters, that's what our first aim. DCT analysis, it's very close, because we assimilated this data anyway. 5 minutes forecast, 10 minutes forecast, 15, 20, 25, 30 minutes forecast. You see the difference? Yes, but not much. Not much, that's good. So we can run this system real time in terms of the computer time. But this system, we still need to improve the computer time. So because we are ending this project, we had to report to the review committee that we had to reduce the resolution. But we did it. We can now run it real time. And it's convincing, because by reducing the resolution, we didn't lose much. That was our final conclusion from this project. Well, part of the reason why we didn't see a lot of impact by these two, probably due to the microphysics schemes, may not be optimal for this 100-meter resolution. So we use the same microphysics schemes that we developed for less than a kilometer resolution. So the microphysics schemes for a kilometer resolution or coarser resolution may not be optimal for a 100-meter resolution. And we don't know what may be the best choice. And if we can increase the computer time for the forecast, we cannot fit it anyway in the timing. So that's why it's OK now. And this has some skill. OK, so R-CCS developed this real-time forecasting system run on the K computer. That's for 5 days, 18-kilometer mesh. And we had a severe rainfall disaster in July last year. And this caused really heavy rain on half of Japan. And we had many landslides and flooding events wide, well, because it's a broad area in Japan. So we used our real-time system. We investigated the data from the real-time system. And this caused more than 200 people died from this. So if you look at the time series, this is July 4th, 0 UTC 12, July 5th, 12 UTC, and it seems that we have the most rain. This is observed rain, the heaviest rain at this time, so we focus on this time. And we run 50-member ensemble prediction to make the probability prediction for heavy rain, more than 50 millimeters rain for 12 hours. That's a heavy rain. And this has a very high scale. We investigated how far ahead of the time that we could predict that event. So investigated the predictability. So when we initialized the prediction on the 2nd of July, 0 UTC, we got this prediction. And 1 day later, 2 days later. So this is good because we had heavy rain like that. And we focus on this box here. And this is not as good because we lose half of this precipitation area. So this, we look more carefully between these two. So we have 1 day separation of the initial time. So we look at every 6-hour separation of the initial time, and we notice that here, at this time, we started get a better forecast. So we look at what analysis increment created the improvement of this forecast and how. So if we compare the 6-hour forecast and the analysis, so this is the analysis increment basically, this pattern made the forecast better. And if we trace the forecast difference in time, this is the time when we have the heavy rain here, close to the time that when we have a heavy rain here, and we could see that this part of the analysis increment grew rapidly and made a big difference between the forecast. So we focus on this part, what caused this analysis increment. So we focus on this area that caused this analysis increment because we apply localization. So we are sure that these observations should impact on this. So we identified that these 4 types of observations existed that time. And we just run a number of denying experiments to investigate the impact of these observations. And so this is the impact of all observations there, all observations that we assimilated. And this is the impact from the satellite wind. And no impact, actually. We removed all of those satellite winds in this region, but no difference. Surface observations, no impact. Ship observations, no impact. If we remove this VAD wind, it's almost exactly the same pattern. That means that this observation, this is a single location radar-based wind profile observation. Single location wind profile observation from the radar caused this difference. So we are pretty sure that this corresponds to the precipitation difference. So this is the forecast precipitation. So this is a control. So if we remove the satellite wind, there's no impact on the precipitation forecast. Or if we remove the surface observation, almost no impact here. Or ship observation, no impact. But you can easily guess if we removed this data, this is 2-day forecast. So 2 days later, this just assimilating this single location wind profile data caused this difference. So we lose this part of the precipitation. Basically, the precipitation shifted towards the southeast.
Where is the wind profile?
Yeah, I can show you. That's in Okinawa, here. That's here. This one. So single location. That caused a big difference. So this was very interesting. Okay, another thing, so this is different topic. Another thing that we explored is nowcasting system. So this is an optical flow so that we just trace the motion tracking. So we can predict like that, and this is the actual observation. So this can predict pretty well. And we have smartphone app, only in Japanese, but you can see this three-dimensional cloud pattern and evolving in time because we do the three-dimensional nowcasting. And it's over 150,000 downloads, so we are very happy to see that. We try to increase. Okay, so I need to accelerate. Okay, let's skip this. So at this moment, we have the next project in our mind that we use. We try to expand the concept of this data assimilation using the actual data from the real sensing system and the simulation. We try to synchronize. But we try to include the human society and economic activities, and we can model some of these activities, and then we can make the prediction, and then we can control, actually, wherever possible. At this moment, it may not be reasonable to develop a system to control the real nature system, but we can easily control our human society. So how to react to these predictions. And we have a range of uncertainties, and we need to make the decision based on the uncertain prediction. So that kind of system that we try to expand. So that's a more general combination of the cyberspace and real world. And we have a system to synchronize for the nature system. So if we expand this system to include more components, we can make the prediction and control. I put AI here because of many reasons I can tell later personally. So we have this data assimilation and what I'm doing now here. So we also try to expand the application of data assimilation to different fields. Because I'm working here at RIKEN, weather prediction or the meteorology is really minor part of this whole RIKEN Institute. RIKEN Institute has like 3,000 researchers and more than 300 PIs. Most of them, only 2 PIs, including me, are working on meteorology, only here. So we have many collaborators in RIKEN and also even beyond RIKEN. So we have biological scientists or different fields, including a social science or engineering applications. So we try to expand the application of data assimilation so we can make the prediction or the simulation. So there are more, because of the advancement of the supercomputing, we can make more realistic simulations for many different application fields. So once they start making better simulations, those people start looking at the real data and compare with their simulation to improve the simulation. That happened in the numerical weather prediction in the history. This is right at 60th anniversary of Japanese operational numerical weather prediction. The JMA started having IBM 704, that's the early time computer, in 1959. That's 60 years ago. And I think the data assimilation started to grow like about this 30 years period. What happened in the first 30 years? They needed to develop the model. They needed to develop more accurate model. Otherwise, the initial condition doesn't matter. The model became more accurate. That's why the initial condition made the difference in the forecast. If the model has a lot of errors, the huge errors, then any initial condition will end up with the erroneous forecast because of the model quality. So that happens to many different fields right now because they require more computational power. For example, if we consider engineering applications, if you would like to, let's say, simulate the combustion system, it's really complicated chemical processes inside, and they have really lots of model error. But now they can make really realistic simulation, look like real combustion process. Then they start looking at the real data to compare with. That's the starting point of data assimilation. That's why I believe that it's now the time to grow, even beyond meteorology. That's what we are looking at. So the first thing that we started to do is to this forest simulation. So we simulate each individual tree. And in the broader area, so we have all of these individual trees. We cannot observe everything, but we can observe leaf area index from the satellite. And we did data assimilation, and it worked very well. So we have not exactly the individual tree corresponding to the real nature, but at least we can represent the satellite observed leaf area index. And we have all trees there. That's nice. And another thing is this pest-forming simulation that's completely different from meteorology. But we have this simulation system. The problem is that it's not very accurate. Well, it is realistic. But we have these problems in press forming. We have spring back, so if we press, then it will go back to the original shape, try to go back to the original shape, and it's really difficult to predict how much going back to the original shape. And those things, we need to improve the, well, basically we need to estimate the model parameters accurately based on the sensor data. So that's what we can do with data assimilation. So these are the things that we explore here at RIKEN with the scope to create the new prediction science. That's what we call the fifth science. The first science is the experimental, and the second is the theoretical science, and the third is the simulation or the computational science, and the fourth is known as the data science. So the fifth science combining the simulation and data science through more involvement of pure mathematics. That's really the key issue, I think. We could develop something for the prediction. Thank you very much for your attention. There are any questions?